Okay, so the last time we talked about the lead compensator, so this time we'll be talking about the lag compensator. Okay, so the lag compensator, most of the times the lag compensator is used to enhance or to improve the steady state error. And this is why it's important to do some steady state error analysis in this exercise. Okay, so let's just make a quick review here. So as we know, the structure, the main structure of the lag compensator is exactly the same as the lead compensator. The only difference is that this time the ratio between the zeros and the poles, the zero is greater than the pole. It's the other way around, not the pole is greater than zero as in the case of the lead compensator. Okay, so let's start our analysis. Okay, so if we want to calculate the steady state error, so we can just use this block diagram here, and we say that, okay, we know that error is equal to the reference, okay, minus E times GC of S times G of S, okay, right, because we take the path that comes from here, okay, so the E multiplied by GC multiplied by G, and then you subtract that from R, you get E, and then you rearrange the terms, so you get something like this, okay, and multiplied by G of S, and this is equal to R of S, and from this expression you can directly say that, okay, so the error is equal to whatever R of S you have multiplied by 1 over 1 plus GC of S times G of S. Okay? Alright, so if we want to calculate the steady state error, okay, we know from the final value theorem that we derived some time ago, we just take the limit when S tends to 0, S times U of S, since we want the steady state of the error. So you obtain the expression of the error, the Laplace transform, and obtain the steady state expression of the error. Okay, I know that might not be clear so far why we are doing this, but it will become clear very soon. So if you multiply S times U of S, and let's say we want to analyze this for a step input, so let's say that R of S as the step input is equal to 1 over S, so this will eventually be equal to limit when S tends to 0, okay, S times 1 over S times 1 over 1 plus GC of S times G of S. Okay, so we can simply cancel those out and then take the limit when S tends to 0. So okay, assuming that the G of S at S equals 0 does exist, so you can just put G of 0. Okay, so the steady state error will be 1 over 1 plus GC of 0 times G of 0. Okay, and this is where it becomes interesting, because the GC of 0 is, in fact, we know already from here that the GC is equal to K S plus Z over S plus P, so we can just say that, okay, we know that, let's write it again, so GC of S is equal to K S plus Z over S plus P. Okay, so if you want to obtain the GC of 0, so it's just simply K times Z over P. Okay, is that clear so far? Okay. All right. So if you want to write the expression of the steady state error now, so it becomes 1 over 1 plus, okay, GC of 0, which is K times Z over P, multiplied by G of 0. Okay, so if you want to minimize the steady state error, you need to maximize this term. Okay, so for a certain value of K, that means that we need this term to be high, or we need to maximize the ratio between Z and P to be as high as possible. And this is where we said that, okay, this is where the lag compensator is actually doing pretty well, because the lag compensator is actually where the magnitude of the 0 is greater than the magnitude of the pole. So from the S-plane point of view, we can say that, okay, if the pole is here, 0, for example, can be somewhere here. Okay, actually the lead compensator was the other way around. Okay, the lead compensator was the other way around. So if we want to maximize this term, okay, we said that we want the ratio between the 0 and pole to be as high as possible, and for this to happen, we need this 0 to be as further away from the pole as possible. So we can put, for example, let's say we can put the pole at, if we put the pole at -1, so we want the 0 to be, for example, at -10, let's say, if you want to preserve a ratio of 1 to 10. But what is the problem with this, or what is the disadvantage about this? Okay, the idea here is that we would like to improve the steady state error, which is increasing the ratio between z and p, but at the same time we don't want to affect the dynamics of the system quite a lot. Okay, we know that the lag compensator, okay, will have a lagging effect on the phase, as we derived from the lead compensator. So it's, for the lag, it's just the other way around. So the phase, if we plot the phase versus frequency, okay, this is what you get a lag effect, and the lag means that you will actually going to reduce the phase margin a bit, although it might be compensated by the reduction in the bandwidth. But yeah, in general, lag compensators have some sort of destabilizing effect, like, for example, the integrator in the PID controller. So it can improve the steady state error, but it has some destabilizing effect. So what can we do with this? Okay, one thing we can do is that, okay, instead of placing the 0 and pole far from each other, we can try to place them close to each other, such that we preserve the ratio, because we are mostly concerned about the ratio. As we see from here, what's most important for us is the ratio. So let's say if we put the pole at -0.1 and the 0 at -1, maybe that's a bit better. You can even make it better if you put the pole at, for example, -0.01 and the 0 at -0.1. So if you go with this, that means that, okay, so you preserve the ratio between the 0 and pole, which is important, but also at the same time you're going to make the 0 and pole very close to each other. Why is this important? Okay, placing the 0 and pole very close to each other means that they will almost cancel each other. They're not exactly, but they will almost. That means that the pole will have a very small effect on the transient characteristics. Okay, so the placement of the 0 quite close to the pole means that actually it will become it will have a negligible effect on the transient characteristics. Or in other words, to say, okay, if this pole has some mode that decays like this, so the presence of the 0 very close to the pole will make this pole, okay, the same mode will exist, so decay with the same rate, but it's a very small magnitude. Okay, so that's the effect that the 0 has on the transient characteristics, and that's what we want to achieve. So usually when we talk about designing a lag compensator, we try to place the 0 and pole, okay, we try to place them closer to each other and close to the origin, and by this way we achieve the low steady state error, and at the same time we have minimal effect on the transient characteristics, because in general the lag compensator will in general make the transient characteristics a bit worse. So if we can take the gain, which is improvement of steady state error while not affecting the transient characteristics, that would be the most optimal. Okay, so to summarize, we can say that, okay, the lead compensator is mostly trying to enhance the transient characteristics, while the lag compensator is mostly trying to enhance the steady state error, and it might not come as a surprise that in many cases we would like to use some sort of combination between those two, as we will see later. Okay,